Look at this split screen showing a physical scale. On it, atoms of magnesium and oxygen are reacting, but notice how it tips to one side. This outcome contradicts the law of conservation of mass, which states that matter cannot be created or destroyed. The mass of the starting reactants must equal the mass of the final products. This reaction between zinc and sulfuric acid shows a balanced state. Look at the tally table underneath. We have 1 zinc, 2 hydrogens, 1 sulfur, and 4 oxygens on the left side, and the exact same count on the right. Because every atom is accounted for, the physical scale balances. Now, let's go back to our magnesium reaction. This is a skeletal equation. It identifies the chemical players, but if we look at the tally table, we have 2 oxygen atoms on the left and only 1 on the right. The scale tips because an oxygen atom is missing from the final product. A skeletal equation lists the chemicals involved, but it doesn't yet show the exact quantities required for mass to be conserved. To fix this, we must mathematically adjust the quantities until the atoms on both sides match. Let's walk through the math to balance a reaction between iron and water. We only add numbers as coefficients outside these molecule boxes. The internal subscripts are part of the molecule's identity and cannot be changed. Our first practical step is to take inventory. We count the starting atoms for each element and fill out the table. On the left side, we have 1 iron, 2 hydrogens, and 1 oxygen. On the right, we have 3 iron, 2 hydrogens, and 4 oxygens. To balance this efficiently, we target the element with the largest discrepancy first. Here, it is oxygen. To match the 4 oxygens on the right, we place a coefficient of 4 in front of the water molecule on the left. This adjustment also affects the hydrogen. Because that 4 multiplies everything inside the water box, the oxygen is now balanced, but the table shows we now have 8 hydrogens on the left side. Now the hydrogen is unbalanced. Pause the video for a moment, look at the right side of the equation, and calculate what coefficient is needed in front of the hydrogen gas to reach a total of 8. Placing a 4 in front of the H2 molecule on the right brings that count to 8. Finally, we balance the iron by placing a 3 on the left side. With the atom counts equal, we add the physical state symbols, like solid and gas, next to each molecule to describe their form. Balancing equations is a systematic process of tracking inventory until the atomic ledger is perfectly equal on both sides. Some chemical reactions require the absorption of energy to break molecular bonds. This laboratory setup is designed for that purpose, a beaker of water containing carbon electrodes, wired directly to a battery. This process is called electrolytic decomposition. It uses electricity to drive the breakdown of a compound into simpler substances. When we flip the switch, electricity passes through the liquid, breaking the molecular bonds of the water. The hydrogen and oxygen atoms recombine and bubble up around the electrodes as separate gases. The physical experiment follows the balanced equation. As the tally table shows, 2 molecules of liquid water decompose to yield exactly 2 molecules of hydrogen gas and 1 molecule of oxygen gas. The mathematical symbols adjusted on paper predict the exact ratio of atoms breaking and reforming in the physical world. The conservation of mass remains constant regardless of the energy source used to power a reaction. For example, look at the decomposition of silver chloride. When sunlight hits the compound, the absorbed energy causes the atoms to rearrange into solid silver and chlorine gas. The mass that enters a reaction equals the mass that exits, whether the energy source is heat, light, or a battery. To balance any equation, follow these 4 steps. First, box your molecules to avoid changing internal subscripts. Second, build a table to take your initial inventory. Third, target the element with the maximum disparity. And fourth, always check how your changes ripple through the rest of the compound. Use these 4 steps as a checklist. They provide a reliable path to solving any balancing problem. Mastering these foundational rules makes the reorganization of elements predictable and mathematically precise.